Alright, hello class. Today we're going to be talking about trig substitution. And this, I think, really starts to show how powerful substitutions are in general. I mean, we know, of course, U substitutions. We use that all the time. But this is our first look at some of the more advanced substitutions we can use to help us with integration. Okay, so how we go about doing this is it's instead of basically letting U equal something, right? That's how we usually do this. Now our transformation is actually, we're going to be transforming, say, x into some, say, trig value, like a sine of x. Okay, so let's show a motivating example of why we might want to do this and start rolling from there. Okay, so here we have the equation of a top half of a circle, so the top semicircle. Its equation is y equals the square root of 4 minus x squared. And so say we wanted to find the area down here using integration. Now, of course, we could just find the area of this because the area of the full circle is going to be pi r squared. And in this case, this is a semicircle of radius 2. So the area of the full circle is 4 pi. Okay, so the area of the semicircle, okay, is going to be just that divided by 2. So 2 pi. Okay, now, of course, we can do this with geometry. We know how to do this. However, we should be able to also analyze this with an integral. So the definite integral from -2 to 2 of this function, square root of 4 minus x squared dx, we should be able to get 2 pi out from here when we integrate this. Okay, but the problem is right now we have no real way to integrate this particular function here, because unfortunately these guys don't simplify, okay, under the square root. So here's the motivation. So this is an example where this type of integral would naturally come about. Of course, this technique that we're about to develop can be applied to much more complicated things, but it would be really nice. So it would be wonderful if we could get this to be something like the square root of some stuff squared, so that we just get down to some stuff. Okay, so we could actually cancel. All right, and how we do that is actually through trig functions and the Pythagorean identity. So we can actually do this through trig, okay, via the Pythagorean identity. Okay, so let's think about, go back to this as well. So this may look familiar. Actually, if this were underneath a 1, right, and we just had an integral like this is a sine inverse pattern, right? This goes to sine inverse of x over 2 plus c, since here this is a squared minus x squared. So this is the same pattern, except it's not in the denominator, right? It's in the numerator all by itself. However, we're still going to identify this as a sine pattern, okay? So this is still the pattern a squared minus x squared, all right? And so we are actually going to utilize a sine when we do this, okay? So let's clear all this out, and we're going to take a look at just the integral. We'll worry about the definite integral stuff later. And I think it's easier to approach this just with an example, and then we'll kind of detail the strategy after for the more general cases. Okay, here I've cleaned up our workspace just a little bit. And if we remember back to one of our earlier lessons, maybe even the first one we did, we identified this as a sine pattern. Okay, so in this case we have 4 minus x squared, so that makes our a 2 in this case. All right, and here's what we're going to do. And the reason we do it this way is mainly because when we do this, it simplifies and gets rid of our square root here, but often we don't even need to maybe cancel square roots. Sometimes it just cancels fractions, or it just simplifies the problem. So here's what we're going to do. Here's the transformation to use. Okay, our transformation is, I'm going to say that x is 2 sine theta. Okay, so we're always going to do this a sine theta. So a we get from the pattern. Sine comes from the fact that this is a sine pattern. I, of course, forgot my n up here. I guess I got too excited. Okay, and so this is our transformation. And much like when we do a u substitution, we're going to do, well, if x is 2 sine theta, then that means dx, probably should have used my orange here, that means dx is going to be, well, now I'll take the derivative of this. It'll be 2 cosine theta d theta. Okay, so let me clean this up a little bit. All right, so I have now that x is 2 sine theta, dx is 2 cosine theta d theta. Okay, so my dx is going to become a 2 cosine theta d theta. Whoops, I'm off the board there. So there, this dx will become a 2 cosine theta d theta, and this x squared, well, I'm going to put in the 2 sine theta squared. Okay, and when we simplify that, it becomes 4 sine squared theta. Okay, so let's write this new integral. After the transformation, it's going to be the square root of 4 minus 4 sine squared theta. And then the dx becomes a 2 cosine theta d theta. All right. Now you might think, well, haven't we just made the problem worse? And actually, we haven't, because now we can simplify this right here, this 4 minus 4 sine squared, with a Pythagorean identity. Right? We're going to use the Pythagorean identity a whole lot. So let's check out the Pythagorean identity. It may not look like we can use it, but remember, our Pythagorean identity is sine squared theta plus cosine squared theta equals 1. Okay, and I want to rewrite it, so it's cosine squared theta is equal to 1 minus sine squared theta. Okay. All right, so there are a couple ways we could go about doing this. We could factor out the 4 here, and I think that's what I'll do this time. Okay, because if we factor out the 4, we'll get 4 times 1 minus sine squared theta. and then this 2 cosine theta d theta part fits in like normal. And then here, this we can just put in the cosine squared. And then underneath the square root, we'll have two things multiplied together, and then we can just cancel out that square root. Okay? Now, how I'll be doing it after this, okay, what we're really doing is factoring, but another thing you can do is down here, just multiply everything by your a squared. Right? And when you do that, you get that a squared cosine squared theta is equal to a squared minus a squared sine squared theta. Right? So this will just save us some steps later on. So in this case, it would be 4 cosine squared theta is equal to 4 minus 4 sine squared theta. Okay? So this is really the version of this we're going to be using further on. Okay, and that's just to simplify, but you can always just factor and go through it the more the lengthier way, but it works either way. But just to save some steps, I'll be using this version of it as we go forward. Okay, so now applying this, we'll get the square root of 4 cosine squared theta times 2 cosine theta d theta. Okay, and as promised, now the square root of 4 is 2, the square root of cosine squared is cosine. So we'll get 2 cosine theta here. Now I already have a 2 cosine theta d theta, and now this simplifies down to be 4 cosine squared theta d theta. And now this is one of our trig integrals from last time. So this is a trig integral. And remember, if all we have is even powers, we've got to do half angle identities. Okay, but thankfully in this case it shouldn't be too bad because we've only got the one cosine squared here. So our half angle identity with cosine, it'll be 1/2 times 1 plus cosine of 2 theta. Remember, the cosine squared goes to the plus d theta. And now this should be integrable and should be fine. Thankfully that 1/2 becomes 2 when we're multiplying the 4 by it. And actually I'm going to just go ahead and move that outside as 2 times the integral of 1 plus cosine of 2 theta d theta. Okay? Now, from here, we just integrate. So it'll be 2. The integral of 1 is just theta, plus now the integral of cosine of 2 theta is going to be 1/2 sine of 2 theta plus c. Okay? Now I'm going to go ahead and distribute that 2 over to get 2 theta plus, and now the 1/2 cancels, so that makes that a little nicer. And there we go. Okay? We're not done yet, though. It might feel like we're done. However, remember what our transformation was. Our transformation was x is equal to 2 sine theta. We started in x's all the way back up here, so we need to end in x's. Okay? So we need to be able to translate back. There's a problem, though. Okay? There's a big problem because we know what sine theta is. Okay? So we need to be able to translate this back. Okay? So before we do that, though, I have a tip for you. Okay, what will make this a lot easier, if you ever get down to sine of 2 theta, what you're going to want to do is use an identity. So you want to use this double angle identity. Let me write it over here. There's a double angle identity for sine. Sine of 2 theta, we can rewrite as 2 sine theta times cosine theta. Okay, so that will make things a little easier on us, and you'll see why, hopefully, in just a second. But I want to rewrite this as 2 theta plus sine of 2 theta plus c. Okay, now, oh, whoops. I totally went against what I just said. I want to rewrite it as 2 sine theta cosine theta plus c. Okay, now what's nice about this is if we scroll back up, okay, our transformation 2 sine theta is x. All right, so I know that this 2 sine theta is just going to be x. All right, but what we need to deal with now are these other two pieces, this cosine theta and this just theta all by itself. All right, so what I'm going to do, I'm going to simplify the workspace a little bit, get rid of some of this work, and show you how we approach these two things, because we know what the sine theta is going to give us. Now we need to figure out what just theta is going to give us and what cosine is going to give us. Okay, so here we are. I've cleaned this up a little bit, and I have it down to just the stuff we need to talk about right now. So through the trig sub, we were able to get this answer down here, this 2 theta plus 2 sine theta cosine theta. So as we already discussed, the 2 sine theta, that's just our transformation. That's going to go right back to x. How we find the cosine theta? Well, we need to use a reference triangle. So to translate back, we often need a reference triangle. Okay, so remember those back from the trig inverse section? It's very closely related. So we are going to make a reference triangle from our transformation. So I'll say built from our transformation. Okay, and what do I mean by that? Well, if we have that x is equal to 2 sine theta, if I move this 2 over and get that x over 2 is equal to sine theta, well, remember, sine is on a right triangle, opposite over hypotenuse. So in a similar fashion that we did before, that's going to make our x the side opposite and our 2 the hypotenuse on our reference triangle. Okay, so if we make our reference triangle, and I put theta here, the side opposite, well, that's going to be x from our transformation, and the hypotenuse will be 2. And now to find cosine, well, remember, cosine is adjacent over hypotenuse, so we need to find the side adjacent. Okay? So to do that, we're going to use our good friend, the Pythagorean theorem. Notice a lot of Pythagorean stuff going on here. And 2 squared is equal to x squared plus the side adjacent squared. And then we'll move this over. So we'll get 4 minus x squared is equal to the side adjacent squared. Okay. And we are going to take the plus or minus square root of 4 minus x squared is equal to our side adjacent. And here we are just going to choose the positive version. Okay, just to, I could go into details there why, but just for our purposes here, the minus isn't really going to do much for us. So we're just basically assuming that our theta is in quadrant 1, and you know, that's how we sort of set things up for ourselves. We created this sine theta ourselves, so we can dictate that, okay, I want the theta in the correct quadrant that we want. Okay, notice what we have here. This is what we started with here. That you are going to see every time. In fact, you often don't really have to do the Pythagorean theorem every single time once you get the hang of how this process works. Okay, it's actually kind of neat how all this works. Of course, I might be a bit biased there. All right, so anyway, so there's 2 sine theta, it becomes the x. Now we have enough information to fill out the cosine piece because we have the side adjacent. So our cosine, let me match it with what we did for our triangle. Our cosine is going to be the side adjacent, which is the 4 minus x squared underneath the square root, okay, all over the hypotenuse, which is 2. Okay, so that's what our cosine theta is going to be. And now the last piece we have is this 2 theta. Okay, well, the 2 theta we can actually get with an inverse trig. All right, so if we go back to this version of it, all right, let me rewrite this. Do it over here. Okay, if I have x over 2 is equal to sine inverse, or excuse me, sine theta, we take sine inverse of both sides. So we get sine inverse of x over 2 is equal to sine inverse of sine. So here's another reason why we can basically choose the positive one, because we're dealing with the sine inverse. That means our, we're only looking at thetas in either between negative pi over 2 to pi over 2. Okay, all right. So this cancels down to give us that sine inverse of x over 2 is equal to theta. So we can just replace this theta here with the sine inverse of x over 2. Well, hopefully this looks familiar. This is actually what happens when we have the 1 over this thing. Okay, this ended up just popping up following the same pattern. All right, so when we simplify this all the way, when now we plug everything in, get it all in terms of x's, we will have 2 times sine inverse of x over 2, okay, plus 2x times the square root of 4 minus x squared over 2 plus c. Okay, now these 2's cancel nicely, so I'll just get rid of it and say our final answer is 2 inverse sine of x over 2 plus x times the square root of 4 minus x squared. And there we go. Okay, so how this process works is essentially we take, or we look for the same patterns that we would have seen in our inverse trig thing, and then do a transformation involving that a and the proper trig function. Okay, I'm not going to integrate this back to, or sorry, differentiate this back to see if the integral actually holds that way. Okay, but what I will do is we'll look at another example to see if this technique lines up with what we already know about the inverse trig functions. All right, so let's take a look at that. For example, here, this integral of 1 over the square root of 9 minus x squared, we already know, okay, so we know that this comes out to be sine inverse of x over 3. Right? Because here our a is 3. And remember, sine inverse doesn't put the 1/3 out front. That would be tan inverse and secant inverse that do that. Okay, so we already know what this should be, but I want to see if a trig substitution gets us to the same thing. And if it does, that helps verify, at least to me, that it actually works the way it should. So let's verify that a trig substitution gives us the same thing. Now what I'll say is we normally wouldn't bother with a trig substitution here because we already know the rule, but it's still good practice. So our trig substitution here, our a is 3, so the substitution we'll use is that x is equal to, remember it's always a, well in this case it's a sine of theta. Okay, this is a sine pattern, right? It won't always be a sine theta, but that's just because it's a sine pattern. So it'll be 3 sine theta. Okay, and that makes dx equal to 3 cosine theta d theta. All right, so when we make our new integral here, it'll be 1 over the square root of 9 minus, now when we square this, so this tells me that x squared is going to be 9 sine squared, right? Because we just square this whole thing. So we'll get 9 minus 9 sine squared theta underneath the square root. And then our dx becomes this 3 cosine theta d theta. And I'm going to put the 3 cosine theta up here. It really doesn't matter. Just to save us some horizontal space. Okay. Now, we're going to use the Pythagorean identity. And I'm going to use the quick one, which basically is that this just becomes 9 cosine squared theta. Okay. So, when we do this, we'll have the 3 cosine theta up on the top. That doesn't change. But underneath the square root, it becomes 9 cosine squared theta. Okay, d theta. And now this can actually simplify down to be 3 cosine theta all over. This simplifies down to just 3 cosine theta. Well, isn't that nice? That all just cancels out. And so what we have is the integral of 1 d theta. So integrating 1 with respect to theta is just theta plus c. And so what we're going to do is we don't need a reference triangle here because we're just going to use the fact that if x equals sine theta, and actually here it's 3 sine theta, sorry, 3 sine theta, that means x over 3 is sine theta. Okay, which tells us that sine inverse of x over 3 is theta. Okay, so we can put that in for our theta. So our final answer is sine inverse of x over 3 plus c. Okay, which is what we already knew we were supposed to get, but this to me verifies that this technique works, okay? Because we took an integral we already know and got the same thing out. All right, so yeah, so there we go. Let's start looking at some of the other transformations, say involving tangent or secant. But before we do that, let's break down all of our possibilities. All right, so here's the breakdown of the three different trig subs that we have, okay, and in relation to their pattern. So, like before, I said that this a squared minus x squared, that's a sine pattern. Well, in this case, we've already seen the examples of this. So, say x equals a sine theta, and then that makes dx equal to a cosine theta d theta, right? And the Pythagorean identity we use is our normal one, but I just multiply them through by a squared. That just saves us some steps. Okay, and here's what the reference triangle looks like. I tend to just build it every time, but when you start to see the pattern enough, you start to realize you can save yourself some time. All right, if you see an a squared plus x squared, well, this is a tangent pattern. All right, and here, much like how we did with the sine pattern, our transformation is just going to be x equals a tan theta, which makes our dx a secant squared theta d theta, because we're differentiating this, and the derivative of tangent is secant squared, and we use this version of the Pythagorean identity, specifically the tan and secant one, which is the same one we'll use for secant transformation. And here's what our reference triangle will look like. I'll go into more detail in the examples where this comes from, but we build it in the same way that we built the other ones. And then finally, here's our secant transformation, say x squared minus a squared. We would use, since this is a secant pattern, okay, we'll use the transformation x equals a secant theta, which makes dx a secant theta, tangent theta d theta, and we use the same Pythagorean identity we do for the tan transformation, and then we get this particular reference triangle. I'm showing you this just because you see that the pattern shows up in the reference triangle. It just shows up in different places each time, but it's still, you should see this, and I think that's a good way to kind of check your work. If this doesn't pop up in your reference triangle, if the same pattern doesn't show up, you've probably done something wrong, and you might want to take a look back at maybe some of your steps to make sure you're doing it correctly. All right, so now that we have this sort of set, let's look at more examples. All right, so here we have the integral of the square root of 1 plus 16x squared. And this is going to be a tangent pattern, but it's not set up in the way we might want it to be. So there are two ways we can approach this. Okay, one, we could rewrite this as 1 plus 4x all squared. Right, so that's one way we could do it. Or, use a different color for this different possibility, or we could actually factor the 16 out. So if we factor out a 16, remember, any place that doesn't have it, we divide by it, and we'll get the x squared all by itself underneath this square root. So that's another way we could do it. So here, that takes a 4 out when we simplify that. And here, that would make our a 1/4. Okay, so that's one way to do it. Or here, this would make our a 1. But when we do our transformation, we would, instead of just x equals, we'd do 4x equals tan theta. Or here, if we did it this way, it would be x equals 1/4 tan theta. And hopefully you see that if I move this 4 over, we end up with the exact same thing either way. Okay, however you decide you want to do it, I mean, that's the transformation either time. Okay, so since it doesn't matter, what I'm actually going to do is just say, well, this is the transformation we'll use, and just throw it right in like that, and show that that just simplifies it anyway. Okay, so let me actually clear this up a little bit and just go straight to using this transformation. Okay, so here we're going to use the transformation x equals 1/4 tangent theta. So then dx is going to be 1/4 secant squared theta d theta. Okay, now this means that if I square both sides, I get that x squared is equal to 1/16 tan squared theta. Okay, so either way, however we decide to do this, this is still going to simplify this down because the 16s should cancel when we plug this in, right? Because we'll be plugging in a 1/16 tan squared theta, and then our dx is going to be become a 1/4 secant squared theta d theta. Okay, so let's write this new integral out as the integral of the square root of 1 plus, I'll go ahead and write it, 16 times 1/16 tan squared theta. And then we'll get 1/4 secant squared theta d theta. Okay, so now we're down to this integral. It'll be 1 plus tan squared theta times 1/4 secant squared theta d theta. All right. So now we're going to use a Pythagorean identity. And typically, this should simplify down to just like a secant. So our Pythagorean identity is, I'll use a different color over here. It'll be 1 plus tangent squared theta equals secant squared theta. Okay, so this just becomes the square root of secant squared theta. And here we'll get 1/4 secant squared theta d theta. All right, so that just becomes secant. So I get 1 secant here, 2 secants there. So this comes out to be 1/4. We simplify this down. The integral becomes the integral 1/4, and then we'll get secant cubed theta d theta here. All right, now we looked at this problem in the last lesson. Remember, we used a reduction formula, and that's probably the quickest way to go about it. So I'm going to apply that reduction formula. Here our n is 3. And we're basically going to get the same thing we got in the last lecture. So I'll go ahead and do that in a step just to save us some time. And it will just appear here. Okay, so here's the application of the reduction formula. And I took the 1/4 all the way out just so I could put this in here without having to deal with it at the same time. But now I'll go ahead and distribute it across. We'll get 1/8 secant theta tangent theta plus 1/8 times the integral of secant theta, which last time we established was the natural log of secant theta plus tangent theta. And having that one down is really going to help with these trig substitutions. Again, I wouldn't give you, say, on a quiz, one where you'd have to know this reduction formula by heart, but knowing that the integral of secant theta goes to ln of secant theta plus tangent theta quickly, that's going to save us a lot of time. Okay? All right, now we want to translate back, right? That's always our main goal, all right? And that's where we build our reference triangle. So if we go all the way back here, remember this is our transformation, and this is what we're going to build our reference triangle with. So let me rewrite that here. that x is 1/4 tangent theta, which we're going to move this over and get 4x is equal to tangent theta. And whenever we do this like this, we're going to pretend like there's an over 1 there. So remember, tangent, that's the side opposite over, not the hypotenuse, but the side adjacent. All right, so it's opposite over adjacent. So when we set up our reference triangle, we'll do that here. Okay, our side opposite is going to be this 4x, and our side adjacent is going to be 1. And when we do the Pythagorean theorem, all right, we're going to get 1 plus 4x all squared, so that'll be 16x squared. All right, and that's, well, that's how it always goes. All right, now when we start translating back, so we know that tangent theta, right, all on its own is 4x. So that one shouldn't be that difficult to translate back. Thankfully, it's not. It's where our transformation came from. It's the secant theta that we need to build. Okay, so secant, right, it's the, it flips cosine around, so it will be the hypotenuse over the side adjacent. Okay, so the hypotenuse is the square root crap, or junk, I should say, over the side adjacent, which is just 1. So I love it when we divide by 1 because it cleans things up. So this secant theta becomes this square root of 1 plus 16x squared. And we're going to pop these pieces right back in here too. So this secant will become a square root of 1 plus 16x squared, and this tangent will become a 4x. All right, so here in this step, let's just put this all back together. Notice this 4 is going to cancel with that 8 and leave us a 2. So it'll just be 1/2 secant theta, tangent theta, okay, plus we'll have 1/8 times the natural log of square root of 1 plus 16x squared plus 4x plus c, and there we go. Okay, that's of course I said all that and didn't even put this stuff back in like I was supposed to. Sorry about that. That should be 4x, and that canceled, so it will actually be x square root of 1 plus 16x squared. Sorry about that. Okay, so there we go. There's that problem complete. Let's look at another example. Okay, so for this example, we're looking at the integral of 1 over the square root of x squared minus 81. Now, what we'll notice here is this is almost a secant pattern, right? To actually get the secant pattern, we need that sort of x sitting out front here, right? That was the full secant pattern. But what we have instead is just the x squared minus the a squared. Okay, in this particular case, our a is going to be 9. All right, so this is a secant pattern. So we're going to let x be 9 secant theta, which makes dx equal to 9 secant theta, tangent theta, d theta. All right, now we're going to put our pieces in here. So here underneath the square root now, the x squared, well, when we square this, it's going to become 81 secant squared theta minus 81. All right, I've kind of made this horrible, didn't I? Let me clean this up. Okay, And then our dx is going to become this 9 secant theta tangent theta d theta. All right. Now we're going to use our Pythagorean identity here. And it's always good to just double check to make sure it works the way you want. So we know our Pythagorean identity for tan and secant is, I'm using a squared here. So 81 tan squared theta plus 81 is equal to 81 secant squared theta. And so if I move this 81 over and get the minus 81, we have 81 secant squared minus 81 is equal to 81 tangent squared. So we can just put in the 81 tangent squared. Okay? You do this enough, you'll start to see a certain pattern that tends to always happen. If it doesn't happen, it probably means you've done something incorrectly. Okay? So we'll go ahead and put the 81 tangent squared in here, and that's going to cancel with our square root, right? So we'll get 1 over 9 tangent theta times 9 secant theta tangent theta d theta. All right, so the tangents cancel, the 9's cancel, and we are just left with the integral of secant theta d theta. Now, thankfully, we've done that work already. We know that the integral of secant is the natural log of secant theta plus tangent theta. Okay, so the secant theta, that's just, we can put in the x value for that, right? So if I don't know if that's on the screen or not. If x is equal to 9 secant theta, that means x over 9 is equal to secant theta. So that means this piece is just going to be x over 9. So no problems there. What we need to do, though, is we need to set up a reference triangle to find the tangent theta. Okay? So for secant, when we set up our reference triangle, so secant, remember, is the opposite of cosine, so it is the hypotenuse over adjacent. So that's going to make our hypotenuse x and our side adjacent 9. Okay, and when we do the Pythagorean theorem, we're going to get the square root of x squared minus 81. Okay, so tangent theta, okay, remember, is the side opposite over adjacent. So this will be the square root of x squared minus 81, and I should probably point out again that this is that same pattern that we started with. All right, that should always happen. If it doesn't, again, something has gone a little off. And then over side adjacent, which will be 9. Okay, so when we put this back in, because if we start with x's, we need to end with x's. So our secant is just x over 9. And our tangent is the square root of x squared minus 81. Okay, all over 9 plus c. And we could stop there. I see nothing wrong with this answer. However, if you're checking your answers in the back of the book or on MyLabs, or you have a multiple choice question that you have to figure out if your answer is the same, okay, what you'll often see is this simplified. So what people tend to do here is they'll, since the denominators are exactly the same, they'll do this. They'll say, okay, it's going to be x plus the square root of x squared minus 81 all over 9 plus c. Then they'll say, okay, inside of an ln, whenever I am dividing, I can split that up as subtraction. So I can say that this is the natural log of x plus the square root of x squared minus 81. Okay, minus natural log the absolute value of 9. And then we let this c absorb this constant. This is just a constant. Okay, so it gets absorbed into c. Okay, so the final answer you will probably see is just this one. The natural log absolute value of x plus the square root. Okay, I don't know what is up with my pen right now. X plus the square root of x squared minus 81 absolute value plus c. Okay, so the thing to note is we can just, if we have the same denominators down here, we can just jump straight to here. You'll see that a lot in this particular class for this particular subject. Okay? All right, so there's that. Let's look at another example. Okay, so in this example, what we'll find is we have a 1 over 1 plus x squared all to the 3/2. So this is our tangent pattern. All right, so this is our a squared plus x squared, and in this case a is 1. So actually our transformation here is not going to be that bad. Since a is 1, we're just going to have x is equal to tan theta, okay, which makes dx equal to secant squared theta d theta. Okay, so let's put that in. All right, we'll have 1 plus tangent squared theta to the 3/2, and then our dx becomes secant squared theta d theta. All right, then using the Pythagorean identity, that's always our next step. That's going to become secant squared. So we have secant squared theta all to the 3/2. Okay, then we have secant squared theta d theta here. All right. Now, secant squared to the 3/2, that's actually going to come out to be the 1/2 power cancels the 2, so we're actually just going to end up with secant cubed down here. So I have secant cubed times secant squared theta d theta, and we actually get some cancellations, right? Secant squared here cancels with 2 of them down here and leaves a 1, so we end up with the integral of 1 over secant theta d theta. Now you might think, oh my god, this is terrible. A 1 over secant theta, how in the world are we going to deal with that? Or you might be saying that if you forgot that secant is just 1 over cosine. So 1 over secant is just cosine. Okay, so we broke this down now into just the integral of cosine theta d theta. And that's going to give us, whoops, nope, sine theta plus c. And here, all we have to do now is make our reference triangle. Okay, so our reference triangle, we're going to use that x is tangent theta, and I'm going to say it's x over 1, right, because that's our a. So tangent is the side opposite over the side adjacent. Okay, so the side opposite will be x, the side adjacent will be 1, and the hypotenuse is going to be 1 plus x squared, as it has been. Okay, so now I need to know sine. Well, sine is the side opposite over hypotenuse. So we needed the hypotenuse to be able to get this. So sine theta is going to be x over the square root of 1 plus x squared. And when we put that in, that's going to be our final answer. Get x over the square root of 1 plus x squared. Oh my goodness. Okay, plus c. And there you go. And actually, that should be enough to get you started on the homework on this section. I'm splitting this into two parts. I'm going to do a second part with more examples for this week. But this is the overall basis. So the next video is really just going to be more examples because there are more things to kind of look at and more complications to deal with. But for right now, that should get you rolling. Okay, so with that out of the way, I'll just talk to you next time. Cheers.